Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you. In this lecture we are going to solve problem 11.1 from the book of Applied Thermodynamics by Eastop and McConkey, chapter number 11, Rotodynamic machinery. So the statement of the problem is the velocity of steam at inlet to a simple impulse turbine is 1000 meter per second and the nozzle angle is 20 degree. The blade speed is 400 meter per second and the blades are symmetrical. Determine the blade angles if the steam is to enter the blades without shock. If the friction effects on the blade are negligible, calculate the tangential force on the blades and the diagram power for a mass flow rate of 0.75 kilogram per second. What is the axial thrust and the diagram efficiency? If the relative velocity at exit is reduced by fraction to 80% of that at inlet, what is then the diagram power? And the axial thrust we have to calculate. Also to calculate all the diagram efficiency in this case. So first of all, we have to discuss the velocity triangles for impulse turbine. This is actually steam impulse turbine. The working fluid is steam over here. So some notation are used and they will be repeatedly used in problem solution of this chapter. So we have to understand it first, that what these notation are used for. For example, starting from here, there are two triangles overlapped on each other. Because CB is common, this is the blade velocity which is common in both triangles. This triangle OBA is actually the velocity triangle at inlet. And this triangle OAC is the velocity triangle at exit of the blade. CAE represent absolute velocity at exit. This is CAE. CAI is the absolute velocity at inlet. Alpha I is the nozzle angle, or it is the absolute velocity angle at inlet. Alpha E is the absolute velocity angle at exit. CB is blade velocity. CRI, it is the steam velocity relative to the blade at inlet. CRE, velocity relative to the blade at exit, where beta I and beta E are blade angles at inlet and exit respectively. So using these notations, first we will write the given data. We have given that the absolute velocity CAI at inlet is equal to 1000 meter per second. Alpha I, nozzle angle is 20 degree. The blade speed CB is 400 meter per second. Blades are symmetrical. It means that beta I will be equal to beta E. Also, further mass flow rate is given which is equal to 0.75 kilogram per second. We have given the value of coefficient of velocity ratio, which is 0.8 K. So for this we have to first find the blade angle beta I or beta E, both angles. The blades are symmetrical, so in this case we will find beta. Similarly, we have to find the tangential force, second, Ft, tangential force. Third, we have to find the axial force, represented by Fa. Fourth, to find diagram efficiency, represented by eta d. When the value of K is 0.8 or 80%, so for that we have to also find when K is equal to 0.8. For that we have to find first the diagram power, second we have to find the axial force, in this case Fa, and third, to calculate the value of diagram efficiency. In first case we will find four things: blade angles, tangential force, axial force, and diagram efficiency. When the value of K is 0.8, so for that we will first find diagram power, then axial force, and then diagram efficiency. So coming to the solution of this problem, to find the velocity values and blade angles, so for that two methods are used. First method is used to draw the velocity triangles up to the scale and find the values graphically from the triangles. This method is used for simple problems. Second method, for complex type problems, analytical method is used, or trigonometric method is used, in which we find the velocity angles and respective velocities. So in this problem we are using the analytical method to find it all values. So first of all, from the triangles, using cosine law of cosine, CRI square is equal to CAI square plus CB square minus 2 CAI CB cos alpha I. First we find the relative velocity to the blade at inlet. We know about the CAI, which is the absolute velocity at inlet, and the blade velocity. So from this we will calculate the value of relative velocity at inlet. So putting the values, CRI square is equal to, the value of CAI is 1000 plus the value of CB is 400. So putting these values, and then the value of alpha I is 20 degree. So simplifying these values, we get 639 meter per second, which is the value of relative velocity at inlet. Now to find the blade angle, for that we will use law of sine. This was law of cosine. So law of sine, from the triangle CRI by sine alpha I is equal to CAI by sine beta I. So putting the values in this, we get the value of sine beta I, rearranging it for sine beta I, rearranging it for sine beta I is equal to CAI by CRI into sine alpha I. So putting the values, CAI is 1000, CRI is 639 is calculated, and sine alpha I is 20 degree. Alpha I is 20 degree. So simplifying this, we get the value of beta. This is actually sine beta. So solving it for beta, we get the value which is equal to 32.36 degree. So this is the blade angle. In this case, as the blade angles are symmetrical, so beta I is equal to beta E, and it is equal to beta, and it is equal to 32.36 degree. So this is the solution of part 1 to find the value of beta. Second, to find other values, for that we will find some other missing values. For example, the change of world velocity, that is delta CW. This is the change of world velocity, and when we have symmetrical blading and there is no shock, so for that we have the expression for the change of world velocity, delta CW equal to 2 CRI cos beta. So putting the values, CRI is 639 and the value of beta is 32.36 degree. So simplifying this, we get the value of delta CW, which comes out 1080 meter per second. So now to find second the tangential force, For that, we have tangential force equal to m dot delta CW. So the value of m dot is 0.75 and the value of delta CW is calculated is 1080. So simplifying this, we get the value of tangential force which is equal to 810 Newton. So this is the value of tangential force, 810 Newton. To find the diagram power for this case, so for that we have diagram power equal to tangential force into blade velocity. So tangential force is calculated is 810 Newton and the value of CB blade velocity is 400. So converting into kilowatt divided by 1000. So we will get the value in kilowatt, which comes out 324 kilowatt. In this case, for symmetrical blading and K is equal to 1, we have axial thrust FA. Third, we have to find the axial force. So for that, axial force, this is 0 because the flow velocity remains unchanged through the blade. We can say that when CFI, the flow velocity at inlet, is equal to the flow velocity at exit, so in that case the axial force is 0. So this is the part 3 of the problem. Part 3 is also, we can say that the diagram power is part 3. We missed it in the required solution over here. To find, also we have given that to find the diagram power. So we can also say that at third point we have diagram power, and at fourth, this is the part 4, axial force. This is third and this is fourth. Fifth, we have to find the diagram efficiency. So for that, diagram efficiency, we have the expression which is 2 delta CW CB by CAI square. Efficiency is nothing but the power developed divided by the energy supplied or the power input. So this is the power developed, which we have seen over here, FT into CB. So this is the diagram power, and CAI is the CAI square by 2 is by basically the kinetic energy of the steam. So this is the input energy, basically our input power. So putting the values delta CW is 1080 and CB is 400. The value of CAI is 1000. So simplifying these values, we get the diagram efficiency, which is 86.4%. Also, with friction in the blades, the relative velocity at exit will be calculated from the expression CRE is equal to 0.8 of CRI. This is the value of K. So, putting the values, CRE will be equal to 0.8. The value of CRI is 639 is calculated earlier. So simplifying this, the value of CRE is 511.2 meter per second. Similarly, the change in world velocity is delta CW. So for this case, when we have K is equal to 0.8, delta CW is equal to CRI plus CRE into cos beta. So putting the values, CRI is 639 and CRE is 511.2 meter per second. Cos beta, the value of beta is 32.36 degree. So delta CW will be equal to 971.6 meter per second. So this is the value of delta CW. Now further, to find the diagram power, for that we have the expression m dot delta CW CB is calculated previously. A diagram power from here, m dot delta CW into CB. Tangential force is nothing but m dot delta CW and into CB. So the same expression is used over here. M dot is 0.75, delta CW is calculated 971.6 and CB is 400. So the diagram power comes out 291.5 kilowatt. So to get the value in kilowatt, we will divide it by 1000. So this is the diagram power, 291.5 kilowatt. Now to find the axial thrust, in this case, it is equal to m dot delta CF. So further it is equal to m dot delta CF is nothing but the difference of flow velocity at inlet minus flow velocity at exit. Further it is equal to m dot CFI is further equal to CRI sin beta minus CRE sine beta. So by applying the trigonometric expression, FA is equal to, further we can write it like this, m dot sine beta into CRI minus CRE. So putting the values, m dot is 0.75, sine beta is 32.36, and CRI is 639 minus CRE is 511.2. So simplifying this, we get the value of axial thrust, which is equal to 51.3 Newton. Now to find the diagram efficiency for this case, again we have the expression 2 delta C W into CB by CA I square. So putting the values, 2 into 971.6 into 400 divided by 1000 square. So simplifying this, we get the value 77.7%. So the diagram efficiency is 77.7%. So in part 2, when the value of K is 0.8, we find the diagram power, the axial thrust, and the diagram efficiency. So we can label it that this is the diagram power, part 1, and this is the axial thrust, and finally we find the value of diagram efficiency. So this is the solution of problem 11.1. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.